I'm Yuchi, coming from University of Michigan. Today, I'm going to show you my latest work about how to use your smartphone to know your touch force without using any additional sensors. So, let's start by talking about these very small but really powerful devices. These devices is nearly indispensable to everyone's daily life. But no matter how big the usage it has, the size of its touch screen is always small. That means the size of the touch screen you can interact with your phone is always limited, it's always constrained to this 5-inch most touch screen. That is the reason many people start to think about using the outer dimensions to increase the capability of a human to talk to their smartphone. What I mean by this another dimension is like even you touch the same area of your touch screen, you might get different responses based on the information of these another dimensions. So this another dimension could be the duration of your touch. It could be the number of clicks you made in your touch, or like the direction how you swipe. And more recently, people start to thinking about using the touch force as one of these another dimension. That is also the focus of this presentation. I will not talk too much how people think it is a good option. The focus of this presentation is how we bring this technology to everyone's smartphone without using any new devices, new hardware. So as what I mentioned before, this technology, the force sensing technology, has gained a lot of attention from the industry, from the academia in the past decades. And finally, in the last year, the Apple announced the iPhone 6s that has this new technology they call the 3D touch. So it's kind of the force sensing technology. They install a bunch of the touch force sensor under their touch screen, so they know how much touch force is applied to the touch screen. Here what I show in this slide is one function they use for this 3D touch. If you click the icon of an application with a lot of force, then you will get the menu of that application rather than going to the application itself. I would say it's kind of a significant step for the force sensing technology. But how about the other devices? How about Android? How about the device you and I just have now? They don't have this specialized touch screen, this fancy touch screen. I mean, even Apple, they announced the cheap iPhone a few months ago. They don't want to install this 3D touch because it's too expensive. A short answer for those questions is you don't need to worry too much now because you have this new technology we call the ForcePhone. So the ForcePhone is a software-based solution that can bring the force sensing technology to nearly everyone's smartphone. Specifically, we have implemented the system in Android and iOS. ForcePhone only uses your built-in sensors, and it's pretty easy. We can also detect the touch force around the phone body. It gives you a very comparable performance like the 3D touch, especially for simple applications, simple tasks, like the hard press button I just mentioned before. I will not go too much. All of those evaluations are going to be presented later. There's one thing I really want to mention, I really want to highlight now. It's please don't think our ForcePhone technology is just a temporary solution. Actually, we create a lot of value to the ecosystem using the force sensing technology. For example, for me, the force sensing technology could be a very intuitive way used as a game control. Like when you play this kind of angry bird with a lot of touch force. That might mean you and your bird is really angry. Yeah, but as you might know now, you don't have this that much application, not much games that are using this technology. Even Apple announced a 3D touch in more than 1 year. The reason for that is simple. Because if I were an app developer, I will not try to design an app just can be played by iPhone 6s and then unable to be played by the other phone. So that's meaning that if we bring this technology to everyone's smartphone, we encourage the app developer to do this more. We're feeling a very important gap between the phone manufacturer, app developer, and also the end consumer. So now let's talk about the secret of our system. The main idea behind our system is based on a very simple but interesting property we call the structure-borne propagation. Here's a simple example of this property. Assume you have a smartphone, you ask your smartphone to play a certain amount of sound by this speaker. Because the sound is a mechanical wave. So actually, part of the energy of the sound is penetrating through your phone body, making a very subtle vibration. This vibration is so subtle, so usually you will not notice about it when you use your phone and play music. But if you monitor the status of the phone by a laser micrometer, you will see at the frequency of the sound that you just played, there's a corresponding phone sound vibration. You can find that in a very small level, usually it's a nanometer level. And more interestingly is, if you now start to touch your touch screen with a lot of touch force, then you will find because you compress the space, the phone can vibrate freely. So actually, this amplitude of this sound vibration is decreased further. If you apply more force, this sound vibration is going to change further. So by monitoring this relationship between the sound vibration change and also your touch force change, we can easily monitor your touch force in the touch screen without using any new sensors. So the whole system we try to build is just with your built-in sensors. So that's the reason we will not use this very expensive laser micrometer. Instead of using that to know the vibration of your phone, we use a microphone for your phone. So the whole system now is like we ask your phone to play a certain amount of sound. We analyze the sound response by your phone and to know how much touch force you have in the touch screen. It's not just that straightforward as what I said before, because actually the microphone and the speaker are not designed for this purpose. So the sound that you receive also includes the sound traversed from the other pathes, like the air pathes, like a reflection, like the echoes. So we should do some kind of signal processing. Most of the detail is just included in a paper. The thing I'm going to present today is just summarize our system based on two very important angles. The first one is how we design the sound we send. The second one is how we analyze the sound we received. Okay. So let's start by looking at how we design the sound we send. Remember, our system is to try to monitor the sound we send. So that means you can choose whatever sound you want. For example, you can send this pure tone. That's simple. You can change the frequency of the sound that you have inside the signal like this. You can also change the amplitude as you want. So we design the sound we send based on three main considerations. The first one is we want to high signal-to-noise ratio when we receive the sound in microphone. So that's the reason we keep using the sound as shown in the middle area of this slide. Somebody call it like chirp. Some people call it the frequency swipe. But the meaning to use this kind of sound is that they have a very high correlation to the sound itself and low correlation to the ambient noise. After you apply the matched filter of this sound, it's pretty easily for you to pick up that's the sound I send and that's not. So you can understand more which part is the sound you sent. The second consideration is we want the signal to be inaudible. So we don't make a noise to the people, we don't bother people. The way we try to do it, firstly, we can increase the frequency of the sound. You use a very high frequency as high as possible that the commodity phone can be used to play. And we found that this high frequency itself is not good enough because actually in the beginning of end of this high frequency sound, you have a abrupt change of energy that make a noise burst like this, pia, 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 pia. So later on, we also make a Hamming windowing in the beginning of the end of signal. That change the amplitude of it. Now the signal has become very smooth. In our experiment, also in our demo like 2 days ago, no people hear the sound. Most people just don't notice. They feel really interesting because they don't know everything. They don't feel the sound we just used. And the next consideration is we want the system to be really responsive. That means once I apply the force, I want to get the signal, the response very quickly. I don't want to get a very long processing delay and get the signal later on. That is the reason we use a very short signal. Short enough, we get enough signal-to-noise ratio. Usually it's a 25 millisecond active signal. We have another 25 millisecond gap between the chirp to chirp, so we don't get confused by different chirps. So as you can see in this slide, that's the final sound we are using. And the next is we're going to show is how we analyze the sound we just sent and then we received to know your touch force. So in this slide, I will just assume we use a very ideal chirp first. Forget about the windowing, forget about the inaudibility, just for illustration now. If you put this very ideal chirp into your devices, and you ask your devices to play this via this speaker, Because the sound is going to go to many different paths and receive it in your microphone. So if you plot the correlation of a signal you just received and the signal you just sent in the time domain, then you will find that will be the result that you will get. You will see many peaks, even you just send one chirp, because the sound goes to very different paths. The first observation is that the strongest peak is usually the airborne propagation sound, because that goes to the direct path, shortest path, and also lose less energy in the air. The following peak should be the echo of the environment, like this sound bounced by the ceiling, bounced by the floor, and received by your phone. Those sounds are not interested into our system. The sound we are interested in the system is the sound ahead of airborne propagation. Because our hypothesis is that we believe the sound in this windowing is actually represented how much sound caused by the vibration. So that's the reason we just made a very easy heuristic. We set up a windowing before the very strong peak, and we calculate the energy of this windowing as an indicator of the force you apply to your phone. For example, if you apply more force to your phone, we expect the energy inside this window is going to change based on your touch force. Things are not going to that easy as what is planned, because that's the ideal case. That's the modeling. Turns out that in the real world, first of all, you want to make the sound inaudible, so you make this windowing, make the sound signal like this. Actually, they break the structure. You make the sound has less correlation to itself now. And the more important is that the microphone and the speaker of a smartphone are not designed for this purpose. So actually make a lot of distortion of the sound that you just send and received. All of those factors combined actually make a receiver sound correlation look like this. Yeah. So the width of the peak is increased a lot. Sometimes it's even larger than the width of the original peak. So it's larger than the windowing we used. So you get a lot of confused. Not only the sound of the vibration, you also get the energy of the sound from the other paths. The way we try to get avoid of this kind of interference from the sound of the other paths is we just monitor. We monitor the sequence of the response over time. For example, remember we keep sending this signal chirp and we monitor different chirp. The key idea here is that we just want to know the change. So we just monitor the relative change of this sound vibration inside this window, even though it might include the noise from the other paths. For example, if you want to know the touch force change in the time t, what we can do is that we keep the windowing signal and we minus the energy of this windowing by some reference point. The assumption of this idea is that we assume the signal from the other paths will not change based on your touch force. So this subtraction actually removes those interference and just keep the energy of the structure-borne sound changes. And usually we set this reference point as a start time of you start to touch your touch screen, because it's relatively stable. Once you start to touch your touch screen, your hand might not change that much position, causing the airborne propagation sound changing. So that's the idea of how we implement the system. Let's look at the result we get. Here's one simple example. I do the force touch under the iPhone 6s. Because the iPhone 6s has a 3D touch, they can understand, give us the ground truth. So first of all, I make a very light touch like this. And that's the response we found by the iPhone 3D touch. The readings from 0 to 1 is normalized based on the Apple's setting. We try to normalize our setting also to fit the Apple setting, so that's the result we get from our system. So as you can see, we got a very similar result. Even though we had a very hard press, we also get a result like this. Later on, I will show you an easy example. It's like we press the phone and we keep continuously increase the force of the phone. And that's the response we get from the Apple as well from our system. There's one thing here you can see that's a yellow line in our figure because Apple actually set a threshold to 1. And our system can also go beyond that threshold because we don't have this constraint now. And all over every information in this slide is showing that the sound relatively change of this vibration, RT we have, actually can represent the touch force in your phone in the touch screen pretty easily. And remember, the whole technology, it cannot be, it's not only designed for a touch screen. It can be only used for many different purposes. For example, we can also know the touch force on the body of the phone now, because as you can see, even you press the body of the phone, you still make the same property. You constrain the phone to vibrate by the sound. One useful application of here is that you might get trouble if you use the phone by one hand, because nowadays the phone is so big. So you might harder to play certain area of the touch screen. Instead of doing that, you might just squeeze the phone twice. Here's the response of the squeeze the phone twice. So by monitor many property, I will just keep that in the paper. You can understand how you squeeze the phone and give a user the proper response. So the important thing here is that the force change, what we monitor, actually we also know the touch force around the phone body. It could be very useful for many new applications. For example, now you also know the touch force on the home button, also the touch force in volume button. Everything is possible now. And here's the evaluation of our system. Due to the time limitation, I will not show all the results we have so far. I will just show the most interesting part of our system. That is, we show the benefit we can get by the end user to use ForcePhone. The way we try to measure it is we actually implement a lot of real testing application. The first one is a mimic like an Apple's application. We call the hard press button. The system is going there to press a fake UI. There's a button. If you click a button, they will just show the application. If you click the button with a lot of force, it will show you the menu option. So it's just the same. The second application we call the ball moving game. It's a generalization of the first one. There's a ball, and then there's a button. If you click the button with different forces, the ball is going to move up and down based on the force you applied. And then we keep increasing the number of the green box. It's a kind of levels, making the game even harder and harder over time. So we show a command saying move the ball to a red box. User going to touch the button to do that. If they finish and accomplish the task, we count that as a successful trial. And the final application is similar to the second one, but we use it to know the user's capability to control the squeeze. We show a command saying squeeze the phone twice. If the user did that, we will change the background to the previous view, so showing like the response to the user. If they don't find the response correctly, they will click this no response button, so we know we failed. So I will show you just a summary of our result we have for the second game now. We show like a probability user can achieve to control the ball to the box with different number of boxes. So the highlight of the result here is that for the 2 to 3 level, the 2 to 3 box, user can pretty easily control the ball based on the ForcePhone technology. So that's good, because we found the most useful application usually just ask a user to control the ball by 2 to 3 levels. If you really want to use the ForcePhone technology to control like the 5 boxes, you probably need to put the phone in a static area, like put the phone in the table, so it can give you more stable reading of the force sensing we made. And then we get a very similar result by the squeeze application. There's only one thing I will highlight here. So the squeeze response, actually the accuracy is changing from person to person, because the different person have a different way to squeeze the phone. Some people might squeeze longer, some people might squeeze shorter. So that's one of our future direction, try to personalize the squeeze detection algorithm, the setting, or even the machine learning parameters, try to feed it to each people, give a better response for them. And then later on, we also recruit even more users. So we don't ask a user's opinion in our previous experiment, because a few participants actually know the technology, know our group. So we just measure how they can control the UI to get the response we set, to finish the task we set. What we are going to here in the user survey is we give this phone to like 21 users in our student building. Those are students, they don't know the technology, they don't know our group. We let them play the game, like our application, for 15 to 20 minutes, and then we give them a paper survey phone. So that's the result we get. The first highlight here is that all of them think the 3 applications we have is useful for their daily life. And they think the system we have now actually is good enough to support the application. And interesting part is that we also ask them to test to use the iPhone's implementation, because we have the same application based on 2 different technology, and we found that many of them actually think our system have a relatively comparable performance to the iPhone's implementation, and we don't need any new hardware. So all the results I show here is actually indicated the really benefit the user can get by our ForcePhone technology. So that's the reason I do like this part of the evaluation, because it shows the real thing user can get. That's the end of this. That's the conclusion of this presentation. Again, ForcePhone is a technology implemented just in software, bringing this force sensing to anyone's smartphone. We use a very new property we call the structure-borne propagation, and the feature of the ForcePhone gives you good enough estimation, and it's used in audible sound and easy to deploy. So that's nearly the end of this presentation. We have talked so far like how we do the ForcePhone and this is smartphone, the small but really powerful devices. But it doesn't mean that our ForcePhone technology is limited to ForcePhone. Remember, in the future, we might have even more small devices, like the IoT stuff, like this smartwatch, smart glasses, smart whatever. All of those devices usually have even smaller interfaces. That would be a good candidate for us to implement. And as you can notice here, most of the devices we show here actually have the microphone and speaker installed. So it's pretty easy for us to install the application. So that's the end of the presentation. I'm so thank you for your attention at attending this presentation.